Hi, welcome to module 15. In this module, we will look at how to use multiplexers to do circuit design. So, we have seen what a multiplexer is in the previous module. We will see how to use multiplexers. So, remember I mentioned that multiplexer is a basic block for designing digital circuits. So, we will see how to use a multiplexer for doing circuit design. So, the first thing that I want to establish, and this is not something that you see in many textbooks, that the multiplexer is actually a universal gate. So, if it is a universal gate, remember that we should be able to get the three basic operations NOT, OR and AND by using the multiplexer and nothing else. So, we earlier showed how NAND is a universal gate. So, in this slide I want to show you how multiplexer is also a universal gate. So, essentially if you are given an infinite supply of multiplexers, that is enough to implement basic combinational circuits. Let us see how. Let us start with the first one. Let us say NOT. I want to see, so there are three inputs, however NOT gate will have only one input. We have to somehow control the inputs in such a way that the function f that we get is just a logical complement of the input. So, one way in which this can be done is as follows. So, whatever input that you want, let us say x, that has to be complemented, you give that as the select line, and when x is 0, you put 1 at the input. For x equal to 1, you put 0 at the input, and this will give you x bar at the output. So, you can see why. So, the multiplexer's function is x bar and 1 plus x and 0, right. So, if x is 0, the output will be 1, if x is 1, the output will be 0. So, that is what we want in the NOT gate. So, we got the NOT ready. Now, let us see how to do OR. To do logical OR, you place, let us say I want OR of A and B. So, you place one of the inputs as the select line, and in the 1 pin you put 1. So, when A is 1, without checking B, you can say that A plus B should be 1, right. So, when A is 1, the output should be 1, when A is 0, the output should be B. So, this is the logical functionality for a OR gate. And finally, for AND, when A is 0, without checking B, you can say that the output must be 0, and if A is 1, the output should follow B. So, this is the logical circuit for a AND gate. So, you can see that if we are able to implement all the three basic operations NOT, OR and AND, so therefore, we can call a multiplexer also as a universal gate. So, the notion of a gate need not be just the basic circuit, sometimes gate is also used for slightly more complicated blocks like these. So, multiplexer is a universal circuit which can do all the three basic operations. So, another useful thing to know is how to implement XOR gate using multiplexer. So, this requires slightly more circuitry. In this case, let us say A and B are the two inputs. So, we know that if A is 1, then we want to give B bar as the output. If A is 0, we want to give B as the output. That is the definition of XOR. So, A XOR B is A B bar plus A bar B. So, when it is A bar, which is indicated by the 0 here, when it is A bar, give B, and when it is A, give B bar. So, this is the way in which you can implement XOR. So, I would recommend that you go and think about whether you can do this without this extra inverter, because I am using another gate here, right, an inverter. Can you try and see if you can implement an XOR gate without using inverters by using only 1 2 to 1 mux? Just can you look at connections that you can do to A, B and so on to see if you can get A XOR B here. You should not use any extra gates nor any extra multiplexers, see if that is possible. So, now let us do a few design examples using multiplexers. So, let us say I am given this Boolean function here. So, W2 and W1, and I have 0 1 1 0. So, you can recognize that this is actually a multiplexer, right. So, when 0 and 1 are different, then you have a 1, when they are same, the output is 0. So, the implementation, let us say I ask you to do it using a 4 to 1 multiplexer. So, there are 4 inputs and there is 1 output. So, there are 4 input combinations possible and there is 1 output. Let us see how to do this using a 4 to 1 mux. So, one way to do that is take your, so remember a 4 to 1 multiplexer has 4 input lines and 2 select lines. So in the 2 select lines I am going to give W2 and W1 as the select inputs, and I am going to take the truth table from here and plug it in here directly, 0 1 1 0, I am plugging it in directly. So this topmost is for the 0 0 pin, there is 0 1 pin, 1 0 pin and 1 1 pin. So there are 4 pins, input pins that a multiplexer will have, a 4 to 1 multiplexer. So I take the truth table and plug it in directly. So this is supposed to realize this XNOR function here, this XOR function here directly. Now you can also realize this using smaller muxes. So I already showed that example earlier, right? So let's do this little bit. So what I'm going to do is I'm going to take the truth table. So this truth table is the same as this truth table here, only that here we used a 4 to 1 mux to do this. I want to see if we can use a 2 to 1 mux, because 2 to 1 mux is actually cheaper in terms of the number of basic transistors in it than a 4 to 1 mux. So let's see how to do that. So if you take this one, you look at the combination here. So you look at 0 and 1 here. If you go and look at W2 and W1, if you don't care about W2 for now, when you can look at it as when W2 is 0, F is W1, right? You can see that here, this 0 1 is the same as this 0 1 here. So when W2 is 0, which is the top half of the table, then F is W1. When W2 is 1, which is the bottom half of the table, F is W1 complement. So you can take this and write it in a different form. So when W2 is 0, F is following W1. When W2 is 1, F must follow W1 complement. So the moment it comes to this, now you can go and write this as a 2 to 1 mux, right? So this is a modified truth table. So in a truth table you will have only 0 and 1 entries, whereas in this truth table you actually have variables. So this is also called a variable entered map, where you don't put all the variables only on the input side, even the function is written in terms of functions of other variables. So W2 is one variable, W1 is other input to the same circuit, but F is not just a vector of zeros and ones, F is some function of W1 also. So this is called a variable entered map, and this is what we had earlier. So we had W2 here, in the previous slide I showed it as A and B, here it is W2, W1. So we give one of the inputs as the select line. For 0 you give W1 as the input, for 1 when W2 is 1 you get W1 bar as the input, and that gives you F. So this is how I came up with the circuit for the XOR gate in the previous slide. So we took the table and modified it to a variable entered map. Once you get the variable entered map, there are only 2 values here. These 2 values you can just put it as a select line, right? Select line, there is only one line which can take 2 values. So we have that. However, if you had this, if you have a 4 entry K map, right? So you have 4 rows here. These 4 rows cannot be expressed only by one combination of W2. For that we needed W2 and W1. That is what we have in the picture at the top. Alright. So now let us look at another example. So in this example we have a truth table which is on 3 inputs. So we have 3 inputs W3, W2 and W1, and there is a truth table that is given here. So let us not worry about what the truth table is supposed to be doing. Let us just look at this idea now. So what we are going to do now is we are going to see if we can use a multiplexer which is smaller in size. So if you directly take this vector and give it as an input to a 8 to 1 mux with 3 select lines W3, W2, W1, and give this vector as the input at the different pins, then you can realize this using a 8 to 1 mux. So I already mentioned this. A function on n variables can be implemented directly using a 2 power n to 1 mux. Now I am going to do something slightly different. So what I am going to do is I am going to take 2 rows at a time. So if you go and look at the first 2 rows, you can see that W3 and W2 are the same, only W1 is changing. So what I am going to do is I am going to write a variable entered map where F is either 0, 1 or a function of W1. So what are the possible functions of W1? You can have W1 itself or W1 complement. So what we will have is in this column we will have 0, 1, W1 or W1 bar. So I am going to take 2 rows at a time. So let us take these 2 rows. In these 2 rows W3 and W2 are 0, so that is what we have here, W3 and W2 are 0. and if you look at f, f is 0 independent of W1. When W1 is 0, f is 0, when W1 is 1, f is still 0. So no matter what W1 is, f seems to be 0, I will write that here, f is 0, so this is independent of W1 when the input is 0 0. Then you look at the next two rows 0 1 0 and 0 1 1. In this case W3 is 0 and W2 is 1. So at least these two are remaining same, but if you go and look at f, f is not 0 like here, it is actually changing with respect to W1. So f takes the value of W1 in these two rows, so you can go and write that as W1 here. Similarly f takes the value of W1 for these two rows, because you are keeping W3 and W2 constant. If you change W1 from 0 to 1, f will change from 0 to 1. So that we represent here. If W3 and W2 are 1 0, then f is W1, and if W3 W2 are both 1s, then without looking at W1 the output is a 1. So even if W1 is 0 or 1, it does not matter, output is a 1, we can write that directly. Once you get something like this, now you go back and look at this, right. So we have now put that in a 4 to 1 mux. What we have done is, now this has 4 rows, so I can use a 4 to 1 mux and implement this. A 4 to 1 mux has 2 select lines, so I will give W3 as this pin and W2 as left pin, as the right pin. So we are assuming that the most significant bit is in the leftmost side and the least significant bit is in the rightmost side. And in the vector here we have 0 W1, which is connecting to both the 0 1 input and the 1 0 input, and finally 1. So it is this truth table entries here directly plugged in. So now if you want to check what the value of f is when, let us say, W3 and W2 are both 1, then you go and look at W3 W2 both 1, that is this pin, so the output is 1. You can see that in the table, if W3 and W2 are both 1, the output is 1. So you can check whether the circuit is correct by plugging in different values of W1, W2 and W3 and go back to the table and check whether it is correct or not. So you have to keep doing some of these things till you get comfortable with the whole idea of translation and so on. So with experience you will get it, but always it is good to, once you get a circuit, plug in the values and check whatever you wanted in the table, is it coming through the circuit or not. Okay. So now there are a few other things that you can do. I will show you how to use a variable as a mux data input. So in general you can implement a n+1 variable function using a 2 power n is to 1 mux. So in the previous slide I said with n inputs you need a 2 power n is to 1 mux to implement it, but actually you do not need a 2 power n is to 1 mux. So for a n+1 variable 2 power n is to 1 mux is enough. So you take n of these variables and give them as select lines, and in the inputs you put 1 0 and a function of the other variable that you have eliminated. So when you go from n+1 variable to a 2 power n is to 1 mux, the input vector can be just function of one of the variables. We will see a quick example later. So in addition to the constants 0 and 1, you will use one variable either in the complemented or the uncomplemented form. So let us see this example. Z of ABC is 3 5 6 7, and what I am going to do is I am going to use C as a mux data input and A and B as select inputs, and if I do that I should be able to implement this using a 4 is to 1 mux. If I directly do this I need a 8 is to 1 mux, because it is on 3 inputs I will need 8 different input lines. Let us see how to do this. So let us look at various combinations. This is the truth table, right. So we have the truth table from A on one side and BC on the other side, and you can see that minterm 3, minterm 5, minterm 6 and minterm 7 are all 1s, right. We have that, and once we have this, right, let us see how to get C out of this. So you go and look at combinations at a time. You look at these two cells here, right. So they both are, so in this case C is changing from 0 to 1, but the output is not changing, the output is remaining at 0. Even when C changes from 0 to 1, the output is 0, so you put a 0 there directly. Here the input, if C changes from 1 to 0, F changes from 1 to 0, which means F is changing as C is changing, so you put a C there also. In these two columns, when C changes from 0 to 1, F changes from 0 to 1, which means f is following c, and in these two cells when c is changing from 1 to 0, f is remaining at 1, which means f is independent of c. So, you have 1 here. So, this is again a variable entered map for 3 inputs, and once you have something like this, you can go and implement that using a truth table, using a mux. So, you can do this, or you could have done something slightly more elaborate. So, I did it directly in the map here. You can also do this from basic Boolean functions. So, you go and look at this. We have a bar bc plus ab bar c plus abc bar plus abc. These are the terms 3, 5, 6 and 7 respectively. In each one of them, remember, because it is a min term, they are all in normal form. So, you can take c out, you then see a bar b, ab bar, ab and so this must have been so this is ab bar, which is 1 0, then you have ab and ab, alright. So, this is from 6 and this is from 7. Then a bar b, in terms of a 2 input setup, you can think about this as min term 1, ab bar would be min term 2 and ab would be min term 3. Right. Then you go and simplify that further, we can write it as c into m1 plus c into m2, then we have c bar plus c into m3, which is same as 1 into m3, right. So, we have the function c and m1, c and m2, 1 and m3, you can rewrite that as 0 and m0, c and m1, c and m2, 1 and m3. So, now if you go and take this and put it into a 4 to 1 mux, so your c will be, so your a and b will be the inputs to the select lines, and the 4 input bits should contain 0, c, c and 1. This is exactly what we saw on the previous thing. So, we saw 0, W1, W1 and 1. So, these are my ABC instead of W3, W2, W1, this is ABC. So, what I just showed is just a way of doing this whole thing using a 4:1 mux. So, you give 0, C, C1 as inputs and you A and B as the select lines, and you get Z as a function of ABC. So, I am trying to show the same thing done in various different ways. Let us see another example. F of ABC is sigma of 1, 2, 4, 7. I want to do this using a 4:1 mux. So, in this case I am going to use variable A as the mux input and B and C will be the select inputs. So, I write it as sigma of 1, 2, 4, 7. These are the terms, and I can take things out. A bar into M1. So, B bar C is equivalent to M1 of a 2 variable function. BC bar is M2 of a 2 variable function. B bar C bar is M0 of a 2 variable function, and BC is M3 of a 2 variable function. So, now you have, in terms of 2 variable things, M1, M2, M0, M3, and there are inputs A bar and so on. Now, you can implement this using a 4:1 mux. You give B and C as the inputs. For input 0 and input 3, A should go uncomplemented. So, the 0th pin and the 3rd pin get uncomplemented versions of A. For minterm 1 and 2, it is supposed to get A bar. So, you put a inverter here. So, A bar goes to D1 and D2 inputs. So, you can go and check whether this is implementing the Boolean function that we needed. So, it is relatively straightforward. So, this way of doing, we will see something called Shannon's expansion at the end of the module. What we are doing is what is called Shannon's expansion. We will see that at the end of this module. So, in general what you have to do is, if you are given a n plus 1 variable function, and if you are asked to implement that is using a 2 power n is to 1 mux, of the n plus 1 inputs, you take n of them and give us select lines, and each combination formed will contain some of these things, will either have 0, 1 or the one variable that you eliminated, right, or the uncomplemented version of the variable that you eliminated. So, each combination of these n variables will select exactly 2 rows from the truth table. So, then you do a truth table to multiplexer mapping. So, what you do is, let us assume that we have the inputs I1, I2, In up to In plus 1 and the function is f. Then what you can do is, you go and look at 2 rows at a time. You take these as select inputs and you take 2 consecutive rows of In plus 1. So, whenever it is 0, 1, if it is 0, 0, then f is 0 itself. If you say that for 0, 1 this is 0, 1, then f is the same as in plus 1. If it gets to 1 0, then it's in plus 1 complement, or if it remains at 1 1, it's at 1. So I am not saying that there is a 4 output function. If f is a single output function and if it takes the value 0 0 for these two rows, then you put a 0. If it's 0 1, you put in plus 1. If it's 1 0, you put in plus 1 complement. If it's 1 1, you put 1. And you do this for every pair of two rows. You take two rows at a time starting from the top, and you do this for every pair of two rows at a time, and you will have to do this 2 power n times. So you will have 2 power n vector at the output, which is in terms of 0 1 and in plus 1. That is the general way to do this. So let us do that as a specific example now. I have given you some function here f, and we want to implement this using a 8 to 1 mux. So it is a 4 input function, which means we should be able to implement this using a 2 power 3 is to 1 mux or a 8 input mux. What we are going to do is we are going to keep the left columns as it is, ABC we are going to keep it as it is, and I am going to take two rows at a time and see what the function f is. So when d is 0 or 1, it does not matter, f is remaining at 1, so I can put 1 here, then this is 0 1 and this is 0 1, so this must be the same as d, then you have 0 1 and a 0 0 here. So for these two rows, even if d switches, f is at 0, so I will put a 0 here, 1 1 will make a 1, 1 0 will make a d complement, 0 1 will make d, and so on, and we have a vector f which is in terms of d now. Now you can get rid of this column d and get rid of this vector here. What you have is ABC and f in terms of 1d d bar and 0. So you take this 1d 0 1 d bar d d bar d bar, you plug that here directly, 1d 0 1 d bar d d bar d bar. You put that in the appropriate pins though. So d naught input should correspond to 1, d1 input should correspond to d, and so on, and the three select lines are A, B and C. You give them in the same order from the highest bit to the lowest bit. That is the order that we have taken. So this is one way in which we can do circuits using muxes. So I am going to show now how to do this in the K-map itself. So let us see this simplified form here. I have used 1d, d bar and 0. Let us see another way to think about the same problem. So what I am going to do is, instead of a 4 variable K-map, I am going to use a 3 variable K-map. So in the 3 variable K-map, I am using only A, B and C. I am not going to use D as an input. And what I am going to do is, I am going to take two rows at a time and I am going to do something different. So in the left top corner of every cell, I am going to put the value of f when d equal to 0 for that cell, and in the bottom I am going to put the value of f when d equal to 1, but corresponding to the combination ABC. So when A is 0, B is 0 and C is 0, for d equal to 0 whatever it is, I am going to put at the left top, when d equal to 1 I am going to put it at the right bottom. So that will be 1 and 1, right. So these are the two values. So this is for d equal to 0, this is for d equal to 1. I am going to do the same thing for the other cells also. So when A is 0, B is 0 and C is 1, it is 0 and 1 here, I put that in the diagonal here. Then for 1 0, it is 0 0, so I put that in the diagonal here, and for 1 1, for this combination, for A equal to 0, B equal to 1 and C equal to 1, that is this set of rows, and I take 1 1 here and put that in the diagonal. I can do that for all the other cells also. Now what we can do is, you go and look at this here. Wherever you have a 1 1, you put a 1, and wherever you have a 0 1, you put a D. Wherever you have a 0 0, you put a 0, right. So 1 1 is a 1. Wherever you have a 1 0, you put a D bar, and you do this for all of them. This table is just a rearrangement of the table that we had here. If we did not have the D column and if this vector here, it would have been a 3 variable K map. The 3 variable K map would end up like this. So this is another way in which you can do this. So now I am going to take you to through other few examples. So at this point I want you to acquire one basic skill. So one basic skill that is needed for you to do a lot of logic design is this. If you are given a K map of 2 inputs, you should be able to recognize whether the truth table given is for AND or XOR and XNOR immediately. So if I tell you that it is a 2 variable K map, if I draw a 2 variable truth table for you. By just looking at the truth table, you should try and guess whether it's AND or XOR or XNOR. These four, if you are able to do, right, it will come in quite handy several times. So I am going to use one of those tricks for this one. So go and acquire this skill. You keep staring at it. It's very easy to actually look at 2 variable AND, 2 variable OR, 2 variable XOR and XNOR. You can recognize them immediately. Actually, it's very easy to pick up. So now I am going to do something similar for this truth table here. So I am going to do something for a 3 input XOR. A 3 input XOR function is defined as W3 XOR W2 XOR W1. We already know what the definition of XOR is. We are taking 3 inputs and we have XOR operators between them. So I am going to do something slightly different from what I did so far. So I am going to take 4 rows at a time. Instead of 2 rows at a time, I can take 4 rows at a time, and if you go and look at these top 4 rows, you go and see what is remaining constant. W3 is held at 0, whereas W2 and W1 are all changing. Right? There are different combinations of W2, W1 we have here. So what I am going to do is I am going to write F in terms of W2 and W1. So if you go and look at the vector here 0, 1, 1, 0 of 4 inputs, you can immediately say that it's actually XOR of, it's an XOR truth table, right? 0, 1, 1, 0 is the XOR of 2 inputs. And what are the 2 inputs here? In this case, W2, W1 are the ones that are changing. So these 4 terms correspond to W2 XOR W1, except that it is for W3 AND, W3 complement. So essentially these 4 entries are W3 bar into or AND W2 XOR W1. If you go and look at these 4 rows here, again W3 is held constant, W2 and W1 are, so if you look at only this part, that's like a 2 input truth table, right. In this truth table you have 1001, that is actually for XNOR. So this is W2 XOR W1 complement. Now we can take this and write it up. So what I am going to do is, I am going to take W3, so look at this part, look at this part. So when W3 is 0, I want W2 XOR W1. When W3 is 1, I want W2 XOR W1's complement. So if I have a mechanism by which I can realize W2 XOR W1, I can then do it from backwards. When W3 is 1, I will give an input which is W2 XOR W1, otherwise I will give its complement. So this part is taking care of the truth table. However, we still need W2 XOR W1, and we know that this is the way in which we can do W2 XOR W1. I already showed this earlier, right. For XOR of 2 inputs, you give W2 XOR W1. So this circuit as a whole is doing W3 XOR W2 XOR W1. Let us take another function here. I am going to call this the 3 input majority function. So we have 3 inputs, and what F is doing is it's taking the majority of the inputs. So you look at the inputs here, if all the inputs are 0, the majority is 0. If all the inputs are 1, the majority is 1. Otherwise, of the 3, if let us say one of them is one value and 2 of them are a different value, whatever is majority, that will be the output. So you take this row here 0, 1, 1, there are majority 1s and a minority 0, so the output is a 1. And if you have, so in this row there are 2 zeros and a 1, so majority is 0 here and so on. This is called a 3 input majority function. So to see what we can, how we can design this using a mux, you go and take these top 4 rows. The top 4 rows, when we combine, you can see that it's actually a truth table for AND. Only the last one is 1, the other 3 are 0. So you can write this as W2 and W1, and you take these 4 rows, if you group them, right, this is the truth table for a 2 input OR, right. So in this case W2 or W1. So when W3 is 0, F is W2 and W1. When W3 is 1, F is W2 or W1. So let us see how to implement this using a mux. So in this case W3 is enumerated, so I will implement that using a 2 to 1 mux. So I give W3 as the select line for a 2 to 1 mux. When it's 0, I want to give W2 and W1 as the input. You can see that here W2 and W1 is going as the input here. When W3 is 1, you want to give W1 or W2 as the input. So this function f is using a mux and two discrete gates and implement a circuit. So these exercises, right, I have been telling implement using only NAND and implement using only mux and so on. There is nothing really holy about using only mux and whatnot. So it depends on what gates you have at your disposal. So if you have 2 to 1 muxes, you can implement the AND using 2 to 1 mux or using 2 to 1 mux and so on. But what if I gave you one AND gate, one OR gate and one multiplexer? So this is an engineering problem. You have to somehow take the problem, decompose that in such a way that you can use the resources that are available and realize the circuit. So what I am trying to show here is you do not have to use 2 to 1 muxes always to do this. In this example, if I had an AND OR and a 2 to 1 mux, it is enough to design this circuit. I do not have to ask for 3 2 to 1 muxes or 1 4:1 mux and so on. I do not need it. So now I will bring you to this famous expansion theorem called the Shannon's expansion theorem. So Shannon's expansion theorem is very useful. So in all the things that I have done so far, I actually use Shannon's expansion without explicitly saying that to you. So let us look at what the theorem says. F of n variables, so it is any logical function on n variables x1, x2, so on up to xi up to xn. So these are a function of n variables. Then I should be able to pluck xi out, which can be any of the xi's. So in this case, we have picked some xi out. So it could be x1, x2, x3, x5, x100, it could be any of them. You can write f as a composition of two functions. So you have xi complement and f of x1 to xn plus xi and f of x1, x2 up to xn, except that wherever it is xi as a variable, you substitute the constants 0 and 1. So you can see it is a very subtle thing, but watch out. So here it is a function on n variables x1 to xn. This term is not a function on n variables, it is a function on n minus 1 variables and a constant 0. Similarly, this one is a function on n minus 1 variables and a constant 1. So we call this the 0 cofactor of f, and this is the 1 cofactor of f with respect to xi. So you take the 0 cofactor of f with respect to xi, and it with xi complement. You take the 1 cofactor of f with respect to xi, and it with xi, logically or these two. Shannon's expansion says you can write this in this form. Why is this interesting? So one way to think about this is, if you go and think in terms of a mux, if I have select bar into something plus select into something, you can see the structure, right? It is very similar. This is, if xi is the select line, then select bar into some f of some n minus 1 input function plus select into f of some n minus 1 input function. So that is why it is interesting. So if you write it in this form, then you can write the output as select bar into d0 plus select into d1, that is a 2 to 1 mux. What you can do is you put xi as the select line and put f of x1, x2 so on with a 0 substituted for xi in xn, and f of x1, x2 so on up to, and 1 substituting for xi in xn, give that as your inputs d0 and d1, and that will give you the function f of x1, x2 up to xi and xn. So this is a very interesting thing, and this is a very fundamental theorem. It is very useful in taking a circuit, taking a Boolean function and decomposing that in terms of multiplexers. We will see a quick example. So let us say I have a function wxyz, I want to write it in terms of Shannon's expansion. The first thing I am going to do is I am going to accumulate all the w bar terms together and all the w terms together. What do we have for w bar? So you have this term x bar z is supposed to be a w bar x bar z plus a w x bar z. So you have that, and this x bar y bar also is a w bar x bar y and a w x bar y, so you have that. So you can see this, you put w equal to 0. So let me do this on paper here. So I have this function f, I have written that here. I will evaluate the function at w equal to 0. So this is my 0th cofactor. When w equal to 0, so this term is 0, and this term is 0. So, it is x bar y bar plus x bar z. When w equals 1, you put 1 here, right. So, this is x bar, the second term will be there as x bar y bar, third term will be as z bar, fourth term will be x bar z. Break, start. So, w bar into x bar y bar plus x bar z. So, this is for when w equal to 0 and this is for when w equals 1. You can simplify both of them, x bar y bar plus x bar z remains as it is. This one can be simplified further as x bar plus z bar. So, now you have w bar into function when f when w is 0 plus w into the function when w is 1. So, you can do it in this form. You give w as a select line, you put x bar y bar at plus x bar z at the d0 input, x bar plus z bar at the d1 input. Now, you have to implement these functions also, right. Nobody is going to give you these things directly, you want to implement this further, right. So, I want to break it down in terms of x and y and so on. So, this I am going to write it in terms of x first. So, I take x out, when x is 0 it is y bar plus z, when x is 1 this is 0. So, that is what we have here, and for this part again I am going to do the same thing. When x is 0, then this function is 1, when x is 1 the function is z bar. So, that is what we have here. So, these terms are taking care of one more level. So, we are going to put x as the select lines for these. So, you can see that here x is coming as a select line to 2 muxes. This mux is implementing x bar y bar plus x bar z, and this mux is implementing x bar plus z bar. And now, here we have z bar 1 0, so all these are okay, but we have a 2 input function here y bar plus z. We can now break it down further and get something very similar. So, now if you go and look at what is given to the circuit, I am giving 1 z, y, z bar, x and w. These are all basic variables or their complements and some constants. So, this is okay. So, now this circuit is taking only 1 x, y, z bar, x, w and 0 as inputs. All these are easily derivable. So, we have used Shannon's expansion, and what we have done is we have first removed w from it, then we have removed x from it, and in this one we have removed y from it. So, this will be only a function of z and 1, this will be a functions of only y, z and 1 and 0. Here you will have a function of x, y, z and 1 and 0, if maybe in some examples you may also get 1 and 0 here. So, this is the use for Shannon's expansion. It is a very useful thing. So, the final block that is important for combinational circuits is what is called a demultiplexer. It is inverse of a multiplexer. So, based on the select lines 0 0 0 1 1 0 or 1 1, it will take one single input and place that on one of the 4 outputs. So, if z is whatever input you give here, if you put 0 0, z will be copied to d0, otherwise it will be copied to d1 or to d2 or to d3. The primary difference is all the other ones will get a 0. So, if 0 0 is given as a select line, z is going to go to d0, all the others will be given as 0. Similarly, when this is 1 0, then z will be given to d2, all the others will be kept as 0. So, you can see that it has similarity. So, multiplexer and demultiplexer has some similarity to what we have seen earlier. So, we have seen encoders and decoders, and we are now seeing multiplexers and demultiplexers. They are all related somehow, right. So, I suggest that you go and think about what is this demultiplexer closest to. So, it has one input, it has 4 outputs and 2 extra lines. Go and think about what is the basic block that you have seen before, which it resembles the most. So, this brings me to the end of module 15 of this week 3, and in the next module we are going to look at Verilog, and I am going to use some examples that we have seen so far and show you how to write Verilog code. So, see you in a little while. Thank you.